So this is week 12. We're still on chapter 13 here, so a little bit behind. But tomorrow I had the exam 3 scheduled, but what we're going to do is we're going to do experiment 8 tomorrow. Experiment 8 deals with Lewis structures and molecular geometry. Oops. And so just take a look at that experiment. And then we'll have exam 3 on Wednesday. The last day to drop is Friday with a W. And so this exam is going to be, let's see, am I recording? Yeah, this exam is going to be a lot of multiple choice. And then there'll be some free response. So a free response would be like drawing the orbital energy level diagram. You'll have to do that. And then maybe drawing some Lewis structures. You'll have to do that. What's that? No, fourth shell. Fourth shell.
Excluding the fifth one, right?
Yeah, you don't have to do the fifth shell. Just up to the 4 p orbitals,
Okay.
and you'll be okay.
So we're going to krypton.
Yeah, up to krypton, right? If we filled it all with electrons, but we might not fill all of them, but you should still be able to draw the complete orbital energy level diagram and label it, and you should get the scale somewhat correct, the spacing and the order. And then maybe Lewis structure, and it could potentially have like resonance form and a geometry. Geometry we'll do more of today and tomorrow.
Also, percent yield too?
Yeah, right. Percent yield, theoretical yield, that kind of stuff. Stoichiometry. You aren't necessarily going to have like a challenge problem like that one quiz. There's 2 parts to that quiz. I need to hand that back. The sodium chloride and was it sodium chloride or sodium iodide? I don't remember.
It was hard.
Yeah, sodium chloride and sodium nitrate. Remember that one? Yeah. That's what the original question was with the unreactive sodium nitrate. So that's other stuff that just doesn't react. And then I gave you a second problem, which was kind of similar, except both species reacted, sodium chloride and potassium chloride. You remember that? Yeah. The sodium chloride, potassium chloride one was, you can take a look at that later. Uh-huh.
I have a couple of questions from the lecture notes.
Okay.
One was that for 1 calorie equal for 4.184 joules, is that by definition or is that just estimated?
Now it's by definition. Before it was just slightly off, 4.1845, et cetera, et cetera.
So I assume 1 kilocalorie or 1 kilocalorie is equal to, by definition, 4.184 kilojoules, right?
Yeah, except I would just memorize 1 and then convert everything else to it. And so if I'm looking at the definition or the relationship between the calorie, this used to not be exact. I don't know why they're doing this. This is really weird, but they're changing a whole bunch of these. Like it's like saying, okay, pi, all of a sudden they say, okay, pi, we're going to change the definition. Now it's going to be exactly 3.14. And then all those people who've memorized it to 20 digits, to 50 digits. I know somebody who hasn't memorized it 50 digits. They don't have to memorize it to 50 digits anymore. If they did that, but they haven't done it with pi, but they've done it with a bunch of others. And so now this is it.
Follow-up question. For the constant light, C,
Mm-hmm.
is that 3.00 or 3.00, or is it, or you said 2.998?
It depends on how many sig figs you want. I like 4 sig figs in my conversion factors. The reason I like 4 sig figs is most problems, they give you 3 sig figs. And so it's nice to have 1 extra sig fig in the conversion factor to minimize rounding error. Is sometimes you're off by a little bit, and is that little bit due to rounding error, or is it due to a calculation error? And so to lower the uncertainty, I carry extra digits. So I like 4 sig figs, but most people will do 3 sig figs.
Is by definition or is just
No.
Okay.
This speed of light is kind of a weird thing. I mean, this is so fast, and you think it's so fast, it's just hard to gauge this. But I mean, but then you look at very long distances, like how long does light take to get from the sun to the earth? Do you know?
Seconds.
No, I think it's minutes. Or from the moon to the earth is seconds, order of. But anyway, we'll go.
Now, something that the light patterns that were observed to make quantum theory led to certain laws to the something equation. What was the name of the equation?
Can you repeat that question one more
So
time?
it was a quantum theory taking observations of unusual light patterns.
Yes.
And it led to certain laws of the length equation, of the method of the lengths.
Okay, yeah, that one, it's not absolutely necessary to know. And so you're right, quantum started with unusual light patterns. And so what I was trying to do is just fit this into the typical way we do the scientific method. So we have unusual light patterns, and then what we look for are patterns and trends. But the patterns and trends we try to fit mathematically. And then we come up with a law. The law that they came up with is called the Rydberg law. Rydberg law fit the patterns and trends. There's one other one too. But the Rydberg law is not in Chem 4. This is Chem 1A.
The Rydberg equation, is that right?
What's that?
Rydberg equation?
Rydberg equation, that's what it is. It's mathematical equation, so we call it an empirical law. Empirical law would be a mathematical equation. And then that came up with a hypothesis, right? The hypothesis in quantum mechanics is that energy is quantized. They're forbidden, and when we say quantized, it means they're forbidden and allowed energies. And then that led to the Bohr theory. But the Bohr theory failed and had to be modified to what?
Quantum theory.
Yeah, quantum theory. So this would be the progression of quantum mechanics using the scientific method. Did somebody hypothesize the Schrödinger equation? You know, so some people think, okay, you start off with a hypothesis, but how hard would it be to hypothesize the Schrödinger equation? It'd be extremely difficult. Or, you know, then this whole idea of quantum, this whole, you know, is just unusual. So hypothesizing that is not so easy. And so you don't have to come up with some genius hypothesis. You know, this is a more systematic method. And you don't have to come up with some fabulous theory like quantum mechanics. You could just come up with simple theories that can fit. And so the scientific method, we aren't developing the theory of everything. You know, we're just looking at different systems and then trying to understand those at a deeper level. But this is for quantum mechanics here.
Quantum mechanics goes hand in hand with quantum theory.
Yeah, quantum mechanics, quantum theory, quantum chemistry, quantum, they're words for the same thing. They all mean the same thing. Yeah. quantization versus continuous. Continuous or continuum, those are opposites. Continuum versus quantized.
What was the difference, or what was the?
A continuum is everything's allowed,
Oh yeah.
and quantized, not everything's allowed. Yeah, other questions you guys have, we can cover those now. All right, so just a survey here for PowerPoint. Do you guys like PowerPoint? I had somebody mention they hate PowerPoints. So, do you prefer PowerPoints or do you prefer like written PowerPoints?
I like them both, but I would prefer for you to write on the board because they write the most important things on the board, you know what to focus on, and have the PowerPoints on the side for extra notes.
Okay. Any other comments? Well,
I think I prefer when you write it. It's a little bit more transitional from what you're saying to what you're writing, but I can't always read the writing, so then it's easier to like see the PowerPoint.
okay. Any other comments? So just maybe a quick,
Yeah, if everything on the slides were to translate everything on the test, then I think there's just a lot of information.
on the
Or
PowerPoint.
like bullet points of like, oh, I can review that and everything just come together. Your notes, that notes. That makes sense.
Could you like cross out what's not super relevant to the test? Because sometimes I get a little confused on when we talk about different things, what's going to be on the test and what we're just talking about.
Most of the stuff, it's hard to do that because the test, I can't test you on everything, but you're supposed to know everything for the next class. And so there's stuff that's relevant, but just not enough time on exams to include that. And so,
Or maybe like a study.
the study,
Like-
yeah, the thing about that, and I know I get this a lot, is a study guide, something more concise. But the problem is the same situation where none of the material is supposed to be cut out. All of it's supposed to be relevant. And so the study guide that I always promote is the study guide is there's one additional step in the study process. And the one additional step is to have a set of lecture notes that you have as a study guide. And you think, well, it's just too much stuff. But if you compare it to the book, like the book might be 1,000 pages, but are you going to have 1,000 pages of notes? No, and so it's something that you can actually, if you work at it, can actually memorize. It's not that, there's a lot of memorization in chemistry, so it's not that chemistry is all memorization, but if you have a good, solid foundation that you've memorized, then it's a lot easier to tackle more difficult problems, things that aren't memorized. And so if you could have a good set of notes, that's actually very helpful as a study guide. Now the PowerPoints, I'm not sure how those are, but
Will you get back the grades for the nomenclature test?
today. Speaking of the nomenclature test, I think what I'm going to do is we'll have that was nomenclature number 2. We'll have a repeat, nomenclature number 3. Nomenclature number 3 is this is where you can make up lost points. Like I'll give you partial credit, like 65% credit. So I'll test you one more time. All you have to do is do the ones you weren't able to do. It'll be the exact same test.
Is that bad?
For some, I mean, it was a lot of people actually got 100. Not a lot, maybe about a number of people got 100% on it, all of them. But you know, some people got like 0 out of 0. I didn't give partial credit. That's why. And so that's going to be a hit. And so what we'll do is we'll do exam 3. I mean, if you got for the nomenclature, even if you didn't, you know, even if you weren't one of the ones that got 0, you could still make up some points. But if you got 100, unfortunately, that's it. You won't have to take it though, at least. I think about altogether, well, in this class, I think maybe 2, not sure. I'll give it back, the break. How about questions for exam 3? Any questions for exam 3?
How many questions?
It'll be mostly multiple choice, and then 2, maybe 3 for your response. Maybe I'll throw in a bonus.
Is it hard?
Is it all? I think all tests are hard, you know, because it's hard to prepare.
What would you recommend to study on? Well, I mean, like, say you have like an hour to study, what item would you choose to like look over?
An hour?
Like, okay, 2 hours.
2 hours depends on how many times you flip through your notes. You know, if I had 2 hours to study, I'd go through my notes. It'd probably take me like 15 minutes or something. I mean, and I just do it over and over again. That is if I had a good set of notes or PowerPoints. And then I just memorize everything in there, because at least you have that. And that won't get you through the harder problems, but it'll get you through like the basics, you know, just to get like the passing. And then beyond that, I go through the homework. You know, I go when I was studying for tests, I go through the homework multiple times, and then what I do is I just mentally categorize the homework. You know, all these are similar in this respect, all those are similar in that respect. So that's what I do.
Are you able to post the answers for your exam 3, like the past test one? That helped a lot for the first exam.
Have to check to make sure we're doing it right.
The exam key, yeah. Let me see. I don't know if I made exam key for that one. I'll take a look.
Could we do it together?
We'll go over the study guide.
For another class,
Well, why don't you take a look at it, and then let me know what questions. But take a look. If I make an exam key, then you can just go through the key. When we're trying to do the shape, We start off with the Lewis structure. I'll just do written those for now. And then from the Lewis structure, we figure out something called the electron group or pair. Pair is a misnomer because we can have more than a pair of electrons. So we'll just call it electron group geometry. And so that's the first thing we determine after the Lewis structure, the electron group geometry, or the EGG. EGG. This just stands for electron group geometry. Egg, you're right. And then from the electron group geometry, we get the molecular geometry.
That's MGG.
No, just MG for molecular geometry. From the molecular geometry, we can get things like polarity. That is it polar or non-polar? So, for example, oil is non-polar, and water is polar. If you can't read my writing, let me know. So that's supposed to be non-polar next to oil. And so we figure out things like polarity. Sometimes in other stuff. And so ultimately what we're after is a molecular geometry. We just use electron geometry to take us to the molecular geometry, and so this is most frequently where we stop. So from the EGG, we get the kind of the shape and the angles. Of electron groups. From the MG, we get the shape and angles for the bonded atoms.
For electron groups, what do you mean in it? Electron groups?
Yeah, the electron groups you're going to find are, let's look at the electron groups right now. Okay, let's have some generic atom A. So if we have an atom A, then this would be a single bond group, just a dash. So this goes to, let's say, B. And so single bond. So that's one type. Another type would be a double bond group, in which we'll have two dashes like that. Double bond. And then we could have triple bond.
Like nitrite, right? Or
Not nitrite. Triple bond we see in nitrogen, N2. Also cyanide has a triple bond in there. There is such thing as a quadruple bond, but it's too rare. We're not going to do quadruple bond. And so we're going to stop at the triple bond. But that's not all of the groups. These are the bonding groups here. And then we have groups that kind of don't bond to anything. And that would be a lone pair group. And the final group will be if we just have a single atom. We see single atom when there's an odd number of electrons that don't even out. And if we have a single atom, this is called a free radical. Free radical are also called dangling bonds. It's like a broken bond that's just dangling there. Dangling, dangling, dangling. Bond. And so these are rarer because they're more reactive, and they'll want to react with something. But we have lots of free radicals around. Free radicals are generated in your body, and they can cause damage. You know, we call it oxidative damage because they want electrons. A free radical wants one more electron. So it can cause oxidative damage. Then you don't want free radicals, and so you have things that react with free radicals, antioxidants, those types of things too.
There's bonding groups and non-groups.
Yeah, these are non-bonding groups here. So we have bonding groups and non-bonding groups. The bonding groups are going to be bonded to some atom. They're here. We'll call it atom B. I don't know what B is. We're just making up some atoms here. Whereas non-bonding groups, there are no other atoms there that are bonded. Now, when we have a bonding group, the electron cloud is actually pulled. Let's take a look at some electron clouds here for these different scenarios. So if we have a single bonding group like this, then the electron cloud is going to be pulled in two directions. A is pulling on the electron cloud and B is pulling. And it depends on which one's pulling with more strength. If A and B are equal in strength, then we get a symmetric electron cloud like this. We'll just say that they're somewhat equal. If they're unequal, then it's going to be an asymmetric electron cloud, but we're not going to get there in this case. So let's say it's fairly even tug of war for electrons. Now, if we have a double bond, one thing is double bonds are shorter and stronger because the atoms are pulled together more tightly. And the reason the atoms are pulled together more tightly is we have electron cloud here, and then we have an electron cloud up here as well, and down here. This makes up the double bond. And so what happens is there's more electron or negative charge density that holds the nuclei together here in the double bond versus a single bond. If we have a triple bond, the triple bonds are the shortest and strongest. And that's because we have electron cloud density here in between. We call this sigma, and then we have pi density as well. And so we have this one up here, which is pi. And then we'll have some pi density out here in the front here and behind here in the back. And so we just have more density. Now, when we have a lone pair, the lone pair is concentrated just on the atom, for example, atom A. And so here the electron cloud is concentrated here. And if we have a radical, then we have less electron cloud. concentrated there. So let's just try to draw this here. So again, the shorter the bond, the stronger it usually is. And so here we see increasing bond strength. Bond strength, we have two words for that. We use bond energy and bond strength. The higher the bond strength, the more energy it takes to break it. And so the higher the bond energy, the stronger it is. As we go across. So the first thing we need to do is we need to count how many groups of electrons there are, because when we count the number of groups of electrons, what that's going to tell us is it's going to tell us the overall shape of this. So let's draw some Lewis structures here real quick. Do you know what this is? That's methane. And how many groups of electrons around this? 4. That's correct. I have 1, 2, 3, 4. Now what we do is we look at it one center at a time. And so if I look at this left carbon here, how many groups of electrons around this left carbon?
40.
You would think 4 also, but it's actually only 3
Double bond, right?
because we can't separate the double bond. The double bond has to be taken together. So we have 2 single bonds and 1 double bond. The 1 double bond is considered 1 group. And so this is actually 3 groups. We don't break it apart, but the double bond is going to have more electron cloud concentrated there.
Is it not 5?
3 groups on this carbon. And how many groups on this carbon? 3 groups also. This is called ethene. Ethene. If we had a carbon triple bond, this is what it'll look like here. This is ethine. Ethine has a common name. The common name for this is acetylene. Acetylene is used a lot in welding. And the old miner caps, they used to use acetylene for the torches. But let's take a look at this ethine or acetylene. How many groups around each carbon? 2. Yeah, we can't split up the triple bond, so we got that, and then we got this triple bond here. Now the double bond takes up more space, so maybe I'll just draw it like this here. And the triple bond is going to take up even more space, but we can't separate it. It's just going to be one unit here.
Then in total for ethene and the triple bond, for ethene, would it be 5 groups?
No, we don't count. We never count that way.
Okay, never count together.
Never count them together. We always look at the carbons separately. So we don't look at the sum total of groups. Some of these molecules are huge. If you look at a protein molecule, there could be thousands of atoms in that single molecule.
So if it's a double or a triple, we don't count on multiple times.
No, just was 1, right. This would just be 1 group. Now there are going to be 5 bonding pairs. You're right. 1, 2, 3, 4, 5 bonding pairs of electrons. But still, we don't count it that way. What you're going to do, like, for example, in organic chemistry, what you do here is you count how many pi bonding electrons and how many sigma bonding electrons. So if this were organic chemistry, I'd count this as 3 sigma pairs and 2 pi pairs. The-
Sigma is across, pi is a little bit below.
Yeah, it depends on where the orbital overlap. I mean, you could figure it out in Chem 4 because the orbital overlap,
It's in the center.
yeah, if it's between the two nuclei, that's sigma. So this is a sigma, and then there's going to be one of these pairs is a sigma, and this is going to be a sigma here. So we got 3 sigmas, but we also have 2 pi's. One of the pi's are going to be above and below, so this counts as just 1 pi. And the other pi is going to be coming out perpendicular. And so there's going to be one lobe that comes out and then one lobe that's behind this. And so those are the green pi and the red pi and the 3 blue sigmas. So you would do that in organic because then it's important to know where the electron cloud is concentrated because that could influence reactivity, you know. Certain things can attack the pi electrons. Like you have something that comes in and attacks the pi electrons. Or the pi electrons attack something. The pi electrons are more prone to react. Let's take a look at some more examples here. How many groups here?
4.
Yeah. 4. What are they?
The two hydrogen and the 2 lone pairs.
Yeah, we have 2 single bonds and 2 lone pairs. Which one has more cloud density
Would it be
on the nitrogen?
the 2 lone pairs?
Yeah, the 2 lone pairs, which are concentrated there. That's because the bonding pair are pulled in 2 directions.
That's 2 pairing electrons, 2 pairing groups, but
Yeah. Yeah, all these groups here, these 4 groups are all bonding. 3 groups bonding, 2 groups bonding, so all bonding. But in this case, we don't have all bonding, but all the bonds aren't equivalent. You know, double bonds more concentrated, triple bonds most concentrated here. When we go here, there are 4 groups. But when we look at the groups, we have 2 bonding and 2 non-bonding. Does this look very good to you?
No,
No, why not?
it's only got 7 under nitrogen.
Yeah, it's less than an octet, and so it's not good. This is what we call a free radical, and it's not going to be very happy, so it's going to be reactive, NO2. There's a resonance form for this. What does the resonance form look like?
Which
Just
is
switch the bond.
double bond.
That's the double bond.
Yeah. All right, now what we do is which atom are we going to look at?
Or the nitrogen.
Just the nitrogen here. And how many groups do you count around nitrogen?
3.
3, yeah. Two bonding and
1 lone
lone pair have more cloud density than the free radical have more cloud density than the non-bonding pair?
Compared to the bonding pair,
Yeah.
yeah, it would be more concentrated.
So
But it depends on how the polarity. It would be kind of comparable to, let's say, single bond.
would we safe to say that from group 1 to group 5 that the electron cloud is increasing?
No, because the situation here is 5, 4 would be the most. Actually, 4 would be comparable to 2 and 3. So it would go like this. 5 would be kind of comparable to 1 or 2, around 1 to 2. 4 would be about 2 to 3. And so 2, 3, and 4 are about the same. 5 is probably between 1 and 2, something like that, as far as electron cloud density goes. Here. So I didn't do these in order. It's just that 5 is not that common. 4 is pretty common. Free radicals, we don't do that many free radicals. Like nitrogen dioxide's a free radical here. But there aren't that many. We can try to make 2 octets, or some people don't like that look on nitrogen, so they'll try something like this. Just make one more double bond, and then will nitrogen be happier? No, because this is no good. Do you know why?
It's not mine.
Yeah, now it's exceeding an octet. So this structure isn't. We could exceed an octet if it were a little bigger, like group 3. I mean, not group 3, in the 3rd shell and beyond. So if it were phosphorus, then yeah, it's possible, but not for nitrogen. And so what we say is this. There's a rule for this. The rule is second period, that is second shell elements, cannot expand their octet. All right, now what we do is we treat these groups like balloons. Some balloons are bigger. So in terms of balloons, which of these are the biggest, would you say? Like a triple bond would be the biggest, say, the most concentrated. And then the single bond should be the smallest. And a double bond is something comparable to a lone pair. And a free radical is something maybe between a single and a double. Does that make sense? Yeah, okay. But we're going to ignore that. What we're going to do is we're going to imagine all 3 groups are the same size. And so we're going to go to electron group geometry next, or the EGG.
Why did they name it geometry?
Geometry is for the shape. So first off, when we do the EGG, we look for the number of groups. If it's just one group, it's just a terminal, call it. But so we'll need 2 groups. And then the EGG is like having 2 balloons. If we have 2 balloons, then the geometry it's going to adopt is linear, we call it. And then we get the angle. So I'll use this symbol for the angle. And that's 180 degrees. So ignoring the size of the balloons, if I have atom A here, then the two groups are going to be at a 180-degree angle. So this is group 1, this is group 2. It looks like a p orbital, but it's not a p orbital. Those are two separate groups. Now, what happens if I make one of the groups bigger? Does it change anything? Let's make group 2 bigger. If I make group 2 bigger, will that change the angle? No. If I make group 2 bigger, it has no impact on the angle because it might push it this way more, but then on the opposite end, it's going to push it back the other way. So it makes it the same. Yeah, right. So it doesn't matter what the groups are. If I made the group 2 a lone pair, does that change anything? No, it's still going to be 180. Okay, now if I put 3 balloons, then it's going to adopt a trigonal planar. Planar is P-L-A-N-A-R. No E. Trigonal planar. And the angle is going to be 120 degrees. So if I put 3 groups around atom A, then to minimize the repulsions, they're going to try to adopt a 120-degree angle. And so we'll have 1, 2, 3 groups. And the angles here for the groups, maybe I'll do a different color. All the angles are the same. So between 1 and 3, it's 120, 2 and 3 is 120, and 1 and 2, it's 120. That is if all the groups are the same. Now, if one of the groups is big, then what's going to happen is it's going to distort the angle. But the distortion of the angle is not huge. You know, by a couple of degrees, it tweaks the angle. So maybe 4 degrees.
What was the problem with the repulsion again?
I'm sorry?
What was the problem with the repulsion again?
If one of the groups is bigger than the other group. So if I made group 3 big here, it pushes in group 1 and 2.
It's repulsion.
Yeah, due to greater repulsions, which means the angle is less than 120. And the angle between 1 and 2 will grow. Or 1 and 3, excuse me. 1 and 2 will shrink, 1 and 3 will grow. And so this is subject to distortions depending on how big the groups are. But this is what we call the ideal. Ideal, we ignore the little distortions. If we have 4 groups, then the EGG is tetrahedral. And the angle is going to be 109.5 degrees. This is rounded to 4 sig figs. Rounded to 4 sig figs, to 5 sig figs is 109.48. To 3 sig figs is 109. So how could that be? How could be is because of cascading effect. So this is like taking 109.48, I think it is, or 47, I can't even remember. 109.48. This is 5 sig figs. And if we take that and round it to 4 sig figs, we'll get 109.4. 8 rounds to 109.5. If we round it to 3 sig figs, then we're taking 109.4. 109.4 is going to round to 109. And so this is why it's kind of weird. Now, how do we draw that? We have a standard way that we draw it. It's called wedge and dash. If we draw a normal one, like 1 here, that's in the plane, and 3, actually, 3 will, we'll make this, I don't know, how should I number it? I'll number this 4. 4 here will be in the plane. And so these are going to be at 109 angles here. But yeah, the other 2 are not going to be in the plane. So one of the other 2 will stick out. That's called the wedge. And this wedge is going to be at 109 relative to 1 and 4. And so we'll make this 3 here. So to show this wedging out, we draw hash marks there. Try to shadow it. And so 3 is going to be wedged out, and that's also going to be 109. And then number 2 is going to be dashed in. So we dash that in like this. And then what I'm going to do is, for number 2, I'm going to draw this dotted to try to show it's going in like that. All the angles are 109. So the angle between 1 and 4 is 109, 1 and 2, and 1 and 3 is 109.
That's a pyramid.
Yeah, it's like a pyramid, exactly. And so this is 109, 109, 109. But the angle between 4 and 1 is 109, 4 and 3 is 109, and 4 and 2 is 109. The angle between 3 and 4, 3 and 2, and 3 and 1, they're all 109. So when you look at this, they're all 109. That has a certain symmetry to it. And that symmetry we call spherical symmetry. It's like being inside a sphere or a ball. It looks kind of like a ball. And so this is spherically symmetric. Now, tetrahedral means four-sided polygon. Four-sided polygon. The way you get a four-sided polygon from this is by connecting this. The vertices. And so we end up with four faces on this. Can't see the one behind there that well. One more color. So this is a tetrahedral, but we never think of tetrahedral like this. We always think of tetrahedral as being this. Two in the plane. So 1, 2 in the plane, and then one wedged out and one dashed in. Do you see that? Can you draw this? This is very important to be able to draw. This is with 4 bonding pairs, but you know, we have all the variations of this. So let's take a look at the electron group geometries. What's the EGG for this one? Tetrahedral. That means 109 wedge dash. What's the electron geometry for the left carbon? Trigonal planar. What's the electron geometry for the left carbon here? Linear. For the nitrogen here? Tetrahedral. For this nitrogen? Trigonal planar. Good.
For the one with the ethane one, how do we structure that?
The one with what?
Ethane?
Ethene? Ethene or ethine?
No, ethane.
Ethene. How do we structure it?
So yeah, with the carbon, just you share the middle part?
Yeah. So the way we do that is we just look at one carbon at a time. So the left carbon is trigonal planar because there's 3 groups. The ideal angle would be 120, but one of the groups are kind of bulky, the double bond. And so what that does is it compresses. You think of 3 balloons, and if one of the balloons is bigger, then it compresses some of the angle. So this angle goes down to about 116 degrees. This angle is about 122 degrees because of the distortion. The ideal angle would be 120 all the way around. For right now, just worry about the ideal angle. So 120 ideal. And the same thing with this carbon, 120 degrees ideal. We look at them separately. We don't combine them in any way. Especially when, let's say you had 100 atoms in there that you have to go through. There's no way you'd combine those. You'd just look at them one at a time.
Will this also help us like in forming the Lewis structure?
Yeah. Yeah. Lewis structures, we don't really care about the geometry most of the time, you know. When we draw them, we just want to get some kind of Lewis structure out.
Some molecular geometry?
Yeah, let's look at the molecular geometry next. So, as far as molecular geometries go, we have some choices here. The simplest choice, okay, would be, let's take a look at, it depends on the EGG here, actually. Let's go. Let me just redo this. So first we start off with the EGG, and then we determine the MG. This is the shape of the electron clouds. This is the shape of the atoms. The shape of the atoms is going to be based on the EGG. And this is what we call Vesper. Vesper stands for valence, shell, electron, pair, repulsion. Pair is a bit of a misnomer here because it doesn't have to be a pair. It could be a single electron, it could be two pairs of electrons, like in a double bond, or it could be three pairs of electrons, like in a triple bond, but we don't separate them out. And so this is a misnomer. Really, I would like to change this to not Vesper, but Vesger. Ger for groups. So valence shell electron group repulsions. That's my preference.
So this also includes the radical and the
Yeah, right. Radicals. Radicals aren't even a pair, so do you ignore them? No, you can't ignore them because they're a balloon, but maybe a little bit smaller. But nobody calls it Vesger. Everybody calls it Vesper. And so when I say based on EGG, I'm talking about based on EGG repulsions. So let's look at the scenarios that we're going to run into. So the simplest would be when we have a linear EGG, what is the angle, the ideal angle? 180. And so we might have a BAC, something like that. These could be all the same. It doesn't really matter. It could be AAA, or it could be BAB, or CAC, whatever. But this is going to adopt a 180-degree angle. This is the EGG. Now, when I do the MG, I look at the bonded atoms. So when I look at the bonded atoms, I see I have a C there and a C there. And so when I look at this MG, convert one of these. The MG is also linear. And then when I look at the BAC angle, the BAC angle is 180 degrees. And so the conclusions that we draw, this is a linear MG, and the BAC angle is 180 degrees. Let's say in this case we have a double bond here. Double bonds are shorter than single bonds. So what's the EGG? Linear. What's the MG? Linear. We expect no distortions here, because even though the double bond is going to take up more space, it's a bigger balloon, will it change the angle? No. And so we end up with the same here. What if we have a triple bond? Yeah. Triple bond will be the shortest. 3. But again, we expect linear. What if we have a lone pair?
It would still be linear.
It'd still be linear, but what is this mg? And then what we say is this is a terminal atom. All terminal atoms are linear. If you only have two atoms, those two atoms are always going to adopt linear, no matter if this is a single bond, double bond, or triple bond. Here. So we just end up linear. But what if the EGG were trigonal planar?
Would it also be a trigonal planar MD?
It could be, yeah. So if it's trigonal planar, what's the ideal angle?
120.
120 degree angle ideal. What did I say? Three single bonds. Even if the atoms are different, let's say B and C, there's a difference in the size. Well, we're not really concerned with that. We're more concerned with the bonding pair. And so even with slight differences in the size of the atoms, the angle should be about the same, 120 degrees. Maybe just slight distortion. You know, let's say C is a lot bigger than B. Then I could distort it slightly. But we'll just say it's 120 degrees. You know, regardless of what the atoms are, this is going to be 120 degrees. And when we look at the molecular geometry, just the geometry of the bonded atoms, what shape is that?
Trigonal planar.
Yeah. So this is going to be a trigonal planar shaped molecule. This is the Mg. And the angles we'd expect, even with different sized atoms, we'd expect the angles to be 120 degrees. Because they're all single bonds. And so what are the angles here? The angles would be BAC. BAD, DAC. All of them at 120. Now, what happens if one of the groups is bigger or smaller than the other group? So, an example of that would be, let's make the AB bond a double bond. And the AC will be a single, and the AD will be a single. Now, the EGG will be the same. $120. So the EGG is going to be trigonal planar. And the ideal angle will be 120 degrees. However, we expect some distortions here because the double bond is going to have twice the electron density. It's not all concentrated in the sigma region. There's pi region, so it's going to spread out a little bit. But it's going to be a bigger balloon, and so that could distort things. And so what we're going to do is we're going to come up with an ideal and distorted. Oops. This is flat in a plane. So the double bond is going to have more electron density. And so what that does is it repels B and C, and it pushes B and C into one another. And so the distorted angle here is going to be, it's going to be about a 2-degree distortion. And so this is going to be about 122 degrees if we're going to guess. And this is going to be about 122 degrees. And these angles have to add up to 360, so this is going to drop down to about 116 degrees. That's because this group has greater repulsions. This group needs more space, so it's going to have greater repulsions. It's going to squeeze these two groups in, 122, 122, 116. And so it's about a 2-degree distortion. These are what we call 3 bonded groups here. So when we have trigonal planar, if we have 3 bonded groups, that leads to mg of trigonal planar. The other scenario that we're going to run into is if we have 2 bonded groups and 1 lone pair. And so we'll put a lone pair on A, and then we'll throw in 2 bonded groups. So I'll replace B. I'll leave C and D here. So again, this is going to be trigonal planar EGG. The ideal angle would be 120 degrees ideal. But when we look at the molecular geometry, we're only looking at the geometry of the bonded atoms. This is not linear. It's not linear because of this lone pair. This lone pair, remember the lone pair is concentrated on the atom here. And so what would you call this shape here? Just the purple. I'm sorry? Crab-like?
Parabola.
Parabola? Oh, it's not curved though. It's like that.
Triangle.
Kind of a triangle, but it's not complete down here. You know what we call it? Bent. It's just called bent. Yeah. This is called bent. Some people call it angular, but so the molecular geometry is going to be bent. And the ideal angle is going to be what angle? 180 degrees? It's still 120. It's 120 because of the EGG. The EGG is preventing it from going 180 because you got this group here. Now this group is about equivalent to a double bond, so how much distortion was there in the double bond? Yeah, it's 2 degrees here, 2 degrees here, 4 degrees here. There's only one angle here, and that's the DAC angle. This is just a guesstimate. Guesstimating about 116 degrees. So the DAC, oops, let me go with a different color. The DAC angle is 120 degrees ideal and about 116 degrees distorted. We're predicting the actual angle to be about 116 degrees. Now we don't do lone pair. Heisenberg uncertainty principle says we can't pinpoint the electron, so we aren't going to measure the angle between the electron and C. The electrons are moving around like birds, whereas the atoms are kind of fixed. You know, the atoms don't jump around on us. Like that. All right, so when we have the trigonal planar EGG, then we get the molecular geometry of trigonal planar, or we get the molecular geometry when we have two bonded groups and one non-bonded. Gives us the MG bent. Now we have two different bents. This is bent at 120 degrees ideal. So that's what we have in this table here. When we have linear, it's always linear. But when we have trigonal planar, then we have two possible molecular geometries. So when we have a trigonal planar EGG, now this is showing three bonded atoms, but that's not the case. These sticks represent groups. And so one option is those are 3 bonding groups. And that's going to give us a molecular geometry trigonal planar. The other option is we have 2 bonding and 1 non-bonding. And that's going to give us a molecular geometry of angular or bent. We'll just go with bent, it's shorter. And so this is showing this. Now this is showing it for like nitrogen dioxide that we saw earlier. So let's take a look at that here as a specific example of this. The 2 bonding don't have to be single bonds in this case. And so we might come up with a Lewis structure that looks like this. But is that a good? No, that's not really a good. Lewis structure doesn't have to show the shape. It's deceptive because when I look at the Lewis structure, it looks like the angle, the ONO angle is 180 degrees. The ONO angle is not 180 degrees. What is the ONO angle? 180 is wrong. And that means what we have to do is we have to analyze the Lewis structure here. When we analyze the Lewis structure, we see there are 3 groups. And in order to separate 3 groups from each other as far apart as possible, then it should adopt a trigonal planar arrangement. What's that?
Oh,
Now, there's a resonance form for this. Do you know the formal charge? Let's count the formal charges. Actually, I screwed this up. You see how I screwed it up? I'm in the habit of writing lone pairs. So, what are the formal charges? For a formal charge, I don't count 8 on oxygen. 6 on oxygen. And how many does oxygen give? 6. So it broke even, 0. How about nitrogen? How many do you count on nitrogen?
4.
Yeah, and how many valence electrons does nitrogen have? 5. So it came out 1 short. If it's 1 short, then what charge does it get? +1 or -1? Plus.
How many is that for?
Yeah, it's missing 1 negative charge. If it's missing 1 negative charge, then you're going to have a resultant positive charge because the protons and the electron charge don't balance out anymore. 7. And how many valence electrons does oxygen have? 6. So it has an extra electron. Extra electron means extra negative charge. Just a minus. Yeah, they cancel out. That's why NO2 is neutral. And NO2, nitrogen dioxide, doesn't have a charge, but this news thing come up. All right. So this is not an accurate representation. This would be a more accurate representation of the shape. And when we do the shape, we don't pay attention to the non-bonding. So we use the non-bonding to figure out the basic geometry, and then the shape is going to just be given by the bonded atoms here. This is just one of the resonance forms here. The other resonance form is going to look like the exact same thing, except, yeah, we just flip the double bond for oxygen. I did it again. It's free radical. Remember, it's free radical. All right, and the angle, ideal angle is, again, it's not 180. It's the ideal angle here. 120 degrees is correct. Now, what do we do about the distortions for this? So we have a double bond, but we also have a lone electron here, which is going to be somewhere in between. Then it'll compress these, expand that. So distorted, this might be expanded a little bit. If we treat we'll treat the lone electron like a bonding pair, and so they'll compress that. And so this will expand to about maybe 122 degrees. This is just a guesstimate. Because of the double bond here. Does that make sense? It's just a guess.
For the MG,
Did I write the MG? No, I didn't write the MG. What is the MG called? Bent. Bent. Bent at 120 ideal or 122 distorted.
maybe O and O in angle.
Right. There's only one angle here, so that's why I didn't write it or label it. It's the O and O angle. And we always do the shortest angle. If you did the longest angle, you know, the O and O would be greater than 180 here, but we do the shortest angle between. That's it for trigonal planar. For trigonal planar, we got two shapes for molecular geometry, trigonal planar and bent. For tetrahedral, we have three shapes. The first shape is tetrahedral, the second is trigonal pyramidal, and the third is bent. But this bent is different than this bent. This bent is bent at 109.5, this bent is bent at 120. And it depends on how many bonding pairs and how many lone pairs we have. So if we have 4 bonding pairs, then we have a tetrahedral molecular geometry. It's the same as the electron group geometry, the EGG. Same thing. It looks like this, a ball, spherical. Tetrahedral is spherical in symmetry. However, if we have tetrahedral here, and one of the tetrahedral groups is a lone pair, then it's not tetrahedral. We don't see the lone pair because of Heisenberg. The lone pair is over here, but we see its effects. Its effects are going to repel these down. And so we call this trigonal pyramidal. This is not the same as trigonal planar. Trigonal pyramid forms a triangular-based pyramid. We rotate it down. If we have 2 lone pairs, then again, we don't see those lone pairs, but we see their effect. The effect is it's going to be bent at 109.5. So we look at that bond angle there. And so let's take a look at some examples of these. What's this called? Ammonium. Ion. We don't have. Technically, we don't have to say ion because ammonium is only an ion. Versus for something like sodium, we'd have to say ion. Otherwise, people would know if we're talking about sodium metal or sodium ion. So the first thing is we draw the Lewis structure. What's the formal charge on nitrogen?
Plus.
What's the HNH angle? If I look at the HNH angle, it looks like it is 90 degrees. Is that correct? The HNH angle. Well, it depends on which H's I'm looking at. 90 and 180. If I look at these two H's, that's 90. If I look at these two H's, that's 180. Is that correct? That's wrong. It's wrong. Yeah, yeah, we have to figure out the EGG first. The EGG is not 90. We have 4 groups. Do you remember how to draw 4 groups? Yes. We need to do wedge and dash. All right, now let's look at the angle. What is the angle between these 4 groups? 109. All the angles are the same. And so it doesn't matter which 2 hydrogens you pick. They're all equivalent. And so even though these look like opposite, they aren't 180, that's 109. 109, 109, 109. So it's spherically symmetric. And so the group geometry is 109 in tetrahedral. But what about the atom geometry? Atom geometry is also going to be tetrahedral. And do you expect any distortions here? No. No. And so the molecular geometry is tetrahedral. And the angle is going to be 109 degrees or 109.5 degrees. This is the HNH angle. Okay, let's stop here. We'll take a break and then continue this after the break. All right, the next molecule we're going to look at is this one. What is this called?
That is called ammonia.
Ammonia. Good. What are the angles here?
Angle there, 109. It's still 109.
Yeah, 109 is correct. It does look like it's 90 and 180, doesn't it?
Yeah.
Yeah, that is tetrahedral.
It looks like this is a 180 and then this looks like a 90. But that would be incorrect. Because Lewis structure need not show the correct angles.
This would be a tetrahedral trigonal pyramidal.
Yes. Exactly. That's correct. When we draw this, it's going to be tetrahedral. Now, the electron geometry is going to be tetrahedral. And so we'll put one lone pair up here and then one bond at a 109 angle, and then a wedged out bond here, and then a dashed in bond here. Redraw that wedge. All right, when we have the ideal angle, we treat all four groups the same. And so the ideal angle here is going to be 109 degrees. And that's based on the EGG. The EGG is tetrahedral. And if we assume they're all the same, then that's what we get, but they aren't all the same. In fact, lone pair is going to take up more space than the bonding pair. And so when we look at the MG for this, it's going to be trigonal, pyramidal. It's going to have a triangular base, and there's going to be a pyramid. Now the lone pair, because of the Heisenberg, isn't exactly pinpointed here, but it's going to be trigonal pyramidal with an ideal angle, again, with this would be the H and H angle. And we could pick any of those, they're all the same at 109 degrees. But we might expect some distortions, and so the distorted angle here, what would you predict?
It would, original angle decrease.
Yeah, it decreases. And so what we do is we just predict like a lone pair of 2-degree distortion. So we predict the distorted angle to be about 107 degrees. Yep.
And the guesstimated one is arbitrary, it doesn't matter.
I'm sorry?
The guessed one is arbitrary, it doesn't have to be like a fixed number right now.
Yeah. Yeah, it's just a guess. And so what we see is the purple. We don't see the lone pair pinpoint that, but its presence is there. And its presence leads to this shape. If we didn't have that lone pair, it'd be trigonal planar. But since we have that lone pair, it's distorted down like that. Well, I'm sorry? It's just a guesstimate. The guesstimate is a 2-degree distortion. All right, and then the last case that we have would be for this, NH2 minus. This is not one that you have to memorize, but you might know what it is. What is it?
It's the name of the other day.
Amide. Amide is correct. All the formal charges in ammonia are 0, but in amide, the formal charges are not 0. What are the formal charges on nitrogen? 5 is awfully high for a formal charge. It's minus, yeah. -1. That's because it has 1, 2, 3, 4, and then half these, 5, 6. 6 electrons, it has 5 valence electrons.
There's also,
Okay, yeah, 5 valence electrons, so it has an extra electron.
there's also the
Right. This is going to be tetrahedral bent. And so the EGG is tetrahedral, and it'll be bent. So we can show that here. What I'm going to do is I'm going to draw the 2 hydrogens in the plane of the page. And then one lone pair I'm going to have sticking out of the plane by drawing it solid. And one lone pair I'm going to have dashed into the plane. I'll make it dashed like that. And so this would be a wedged out lone pair, that would be a dashed in lone pair. And so this would be it. And so again, the EGG is tetrahedral. And that's going to set our angle. The ideal angle would be 109 degrees. But the MG is not tetrahedral. The Mg is bent. Yeah. But it's different because the angle on this is different than the previous one. And so the Mg is bent
Do we see
at 109, 109 degrees ideal. Oops. What would you expect for distortion?
increase?
Yeah, and each lone pair is going to distort it by about 2 degrees. And so if we look at one lone pair, it squeezes it in. The second lone pair squeezes it in. And then the angle is going to be decreased to about what?
105.
105 would be the guess. So about 105 degrees.
When does the angle increase again?
The angle increases here. The problem is we don't measure this angle. So the lone pair nitrogen hydrogen angle would increase. So this would be about 111. And the same thing here. This lone pair nitrogen hydrogen angle increases, and then this would get squeezed down. So these angles expand by about 2 degrees. These contract by about 2 degrees. Now for this one up here, it's the same. So this angle expands. The lone pair nitrogen hydrogen angle expands, and then this one contracts. Since we don't do angles between the lone pairs, the angles are always defined by three atoms. And so you need 3 atoms to define a bond angle. This is called a bond angle. So for molecular geometries, Mg, we have something called the bond angle. And 3 atoms. We need 3 atoms to define. And so there's only one bond angle here because there's only these 3 atoms, hydrogen, nitrogen, and hydrogen. All right, so that was the last of the scenarios there. The next thing we're going to look at is polarity. And so what we have is something called the molecular dipole. The molecular dipole is equal to the sum over 3 dimensions of the bond dipoles.
Summation.
Yeah, this is sigma for sum,
What is that on top of it? 3 what?
3D, 3 dimensions. The sum of the bond dipoles over 3 dimensions. If there's if the molecular dipole is equal to 0, then we say it's nonpolar or small, very small. If it's not equal to 0, then we say it's polar.
How do we define small? Very small.
We define it based on the bond. That is, very small means the bond dipoles are less than 0.5 delta ENs. Carbon-oxygen bonds are quite polar. What is the electron geometry? How many groups do we have here? 2, 3, or 4? 3? 2? Yeah, 2 would be correct. 2. We don't do the terminal. It'd be 3 for the terminals. But there are 2 groups.
What was the question again?
How many groups, electron groups, are there? Correct answer would be 2 electron groups. What are they? They're double bond, 2 double bond groups. And so what's the EGG? Linear. What's the MG? Yeah, MG is the same. It matches the. So the MG is linear.
And then you over both of your
Yeah, 180 degrees ideal. Do you expect any distortions?
No.
No. You're right. Okay, then the next thing we're going to look at is it polar or non-polar. So what we do is we do the bond dipoles. And the way we draw the bond dipoles is we draw them towards a more electronegative oxygen here, the arrowhead. Like this. And so we're going to add up these 2 arrows. If we add up these 2 arrows, they'll form one big arrow or a smaller arrow or no arrow. So for example, let's say one oxygen's pulling to the right, the other oxygen's pulling to the left. Which direction will the molecule go? Right or left? It stays the same. So these 2 add up to 0. So this bond dipole plus this bond dipole equals 0. Therefore, this is non-polar. So carbon dioxide is non-polar.
This would be the net, right?
Yeah, the net. And so when we sum these up, the sum of the bond dipoles is equal to 0, so there's no molecular dipole. Okay, let's do another one here. Actually, let's do BF3. What's the name for BF3? No, close. Barium trifluoride. Barium trifluoride. Oh, not barium. Sorry, boron trifluoride. That's correct. Barium, what's the symbol for barium? Ba. And so B just refers to boron. There's a problem with this. What is the problem?
There's no octet around boron.
Yeah, there's no octet around boron. And so one way to fix that is to make a double bond. Are there any formal charges in the structure? No. So if we make a double bond, we'll take one of the lone pairs on fluorine and double bond that to boron. Does fluorine still have an octet, even if it double bonded?
Yeah.
And now does boron have an octet?
Yeah.
Yeah, so what you'd say is this is a win-win.
So like one doesn't.
Right, but it isn't a win-win. Boron wins, but fluorine loses. But it didn't lose its octet. What did it lose? Yeah, it lost its zero formal charge. Before it was a zero formal charge. What is its new formal charge?
It is now maybe plus.
Yeah, on fluorine it's +1. On boron it's -1. Now, the question comes up, okay, fluorine lost to boron, but fluorine's very strong. Is boron very strong? No, boron's very weak. Fluorine is at the top of the electronegativity chart. Do you know what the highest number for electronegativity is? 4. And boron is like a 2. Actually, boron is around 2. And so fluorine's quite a bit stronger. And so this gives us our rule. What's our rule? Fluorine and hydrogen never double bond. I shouldn't. There's some weird stuff with hydrogen, but where it forms 2 bonds, 2 single bonds. But we'll just leave it like this for our structures. So we're stuck here. So what's the EGG? Trigonal planar. Angle for trigonal planar? What's the MG? And angle? Any distortions? No distortions. Is it a polar molecule or nonpolar? It's nonpolar. What we do is we draw an arrow towards fluorine. Fluorine's more electronegative. And the way we think about it is if there's a tug of war here, which direction will the rope go? Towards fluorine, but we have 3. Will it be a 3-way tie, or is one of the fluorines going to win? This is a 3-way tie, so this is nonpolar. When we sum those up in 4.
If we were to have broken the fluorine and hydrogen double bond rule, it would have gone toward above, correct?
This one?
Yeah.
No. This one we have 3 resonance forms. And the 3 resonance forms, the correct structure would be a hybrid, that is an average of the 3 forms. Yeah, and so it would still be the same as nonpolar. This has symmetry to it as well. What's this called? carbon tetrafluoride. If we draw the Lewis structure, again, does not have to accurately show the geometry. And so it looks as if the angles are 90 and 180, but that's not correct because it adopts a tetrahedral, right? Tetrahedral geometry to minimize the repulsions. And so the EGG and the MG are the same. Yeah. Any distortions to the angle? No. And this is non-polar.
So I guess saying non-polarity and distortions go hand in hand, right?
No.
Because it's
It could be ideal and still be polar. What we have to do is we kind of have to add them up. This one's a bit tricky to see, but if we have 4 things, and you want to, let's say this is inside a ball, and you want to distribute the weight inside the ball evenly, then you'd adopt the tetrahedral way. And so this is spherically symmetric. It's going to be nonpolar because the 4 bond dipoles add up to 0. And so the sum of the bond dipoles equals 0, molecular dipole. So it has very polar bonds, but it's a nonpolar molecule. So carbon tetrafluoride is nonpolar. Now, if we replace one of the fluorines with a hydrogen, then it's going to be polar. So let's remove the top one, and we have the 3 bottom ones, then there's going to be a net molecular dipole that's going to point straight down. So let's try that one next here. An example. Let's take that top fluorine and replace it with a hydrogen. Now, if there's a tug of war here, the hydrogen's going to lose compared to the fluorines, since its electronegativity is a lot weaker. That's going to make it polar. And so we're going to have these 3. In fact, the delta En for this is small. It's small enough to ignore, right? Small enough to ignore. Carbon-hydrogen bonds are nonpolar. They are polar, but their polarity is so small that we're going to classify these as nonpolar. In other words, the bond dipole is too small to really worry about. And so we're just worried about the red ones here. Carbon is just slightly more electronegative than hydrogen. And so this bond dipole is so small, it doesn't really do much. But let's add up the 3 on the bottom. When we add up the 3 on the bottom, which direction will the molecule move? Now the molecule is going to move straight down. And so these 3 add up to give you a molecular dipole that goes straight down. And so what we say is that this is a non-zero molecular dipole. Therefore, this is a polar molecule. Now, when we say a polar molecule, it's going to have a positive and a negative end to it. The end with the 3 fluorines here is going to end up being negative. And the hydrogen end is going to be the positive end. That would be it. So I assume everybody's seen this old test, right? I'm going to stop there for chapter 13. That's pretty much the end of chapter 13. And we could take a look at this. Old exam 3. Let me download this. Yeah, I don't think I made the key for this. Did that work? Okay, so some people want to go through this as a mock exam. I don't want to spoil it necessarily, but if it's all right, then we can go through it as well. You want to go through it? Or did you want to try this as a trial? Okay, we're going to go through it quickly because we don't have that much time, so let's just crank through this very fast. Strong oxidizer to weak oxidizer is driving force for double replacement reactions. False. Go with blue. I'm going to keep this as a key. Metathesis reactions consist of favorable ion combinations. A mole of carbon-12 atoms weighs exactly 12 grams. True. That's the definition of carbon-12. AMU. Remember? A carbon-12 atom, a single atom, weighs 12 U. Therefore, a mole of them will weigh exactly 12 grams by definition. 4. If 2 grams of hydrogen is allowed to react with excess, this is supposed to be O2. This is a typo. O2. Then 2 grams of water is produced. 5, the theoretical yield for a reaction was 98.3 grams. The amount actually obtained was 91.5. The percent yield is 91.89. I'll just do it really quick then. Is it C?
91.5 grams is the actual yield, correct?
No, 91.5 divided by 98.3. If you got 100% yield, it would be 98.3. Let's see. What ions are present in what ratio in a solution of aqueous calcium chloride? C is correct. Weak acids are weak electrolytes. True. HF is completely ionized in water. Is HF a strong acid? No, HF is not one of those. How many common strong acids were there? 7. Take a look at the list. Was HF on there? No, HF is a weak acid. Weak acids are only partially ionized. B. 9. Which of the following substances will precipitate from, this is supposed to be from an aqueous solution. D. In the combustion of methane, according to the equation, how many grams of water are formed from the combustion of 4.24 grams of methane? Just do it. 4.24. Convert that. Go from grams to, this is supposed to be grams. Grams. We're going to go grams to moles. So mole methane 16.05. It gives me moles. And then what is it? Water. It's a 1 to 2 ratio. So 2 times 2 moles of water per mole of methane. And then the molar mass of water is 18.02. 9.52. This is going to be the closest. It's off slightly.
On the exam, we just choose.
I got 9 point. Yeah, just choose the closest one. I got 9.52.
Maybe our 6 figs are a little bit short.
Yeah, that could be. Because it's probably round off. 9.51 versus 9.52 is probably rounding error. If it's more significantly different, then I double check my calculation and then double check the answer. Let me try that one more time. So I'll double check my calculation. 424 converted to moles. Then it's a 2 to 1 mole ratio, and then times 18.02. Yeah, 9.52. It's all right. 11. PCl5 can be produced by the reaction of PCl3 plus Cl2 yields PCl5. What mass of PCl3 must be used to produce 127 grams of PCl5 if the percent yield is 84.8%? All right, this one is going to be a little bit more involved, and so I'll probably do this one. Actually, since I can do this, I'd probably do this on scratch paper, but since I can blow this up, I'm just going to do this. And so what we want is 127 grams of actual yield. And I'm going to narrow my pencil then. Since this is just PDF, you can, oh, is that the thinnest? Okay, this is thinnest. We want 127 grams of PCl5 actual yield. Percent yield is equal to the actual yield divided by the theoretical yield times 100%. And so what this is a percentage. So what that means is I'm going to get 84.8 grams actual yield for every 100 grams theoretical yield. All right, then I need to figure out the molar mass of PCl5. So I have phosphorus, which is 30.98. Is that correct? 30. What did you get? 208. I only go 2 decimal places. So let me just recalculate. 30.98 plus 5 times 35.45. You could be more precise. I got 208.23. I would just go 2 decimal places because that gives me 5 sig figs. That's more than enough. PCl5 per mole. PCl5. And then where?
PCl3.
Yeah, the PCl3. So what's the mole ratio? 1 to 1. So 1 mole of PCl3 per 1 mole of PCl5, and then the molar mass. So it's 30.98 plus 3 times 35.45, 137.33. PCl3 is called what? Yeah. Phosphorus trichloride making phosphorus pentachloride. All right, so let's do the calculation. 127 times 100 divided by 84.8. What did you get? Divided by 208.23 times 137.33. 98.77. See. Let me save this.
Can we do the percent yield or the ratio of 100 over 84.8? Can we do that at the end? Like do the whole thing and then where we at 5 times.
Mm-hmm. Yeah, you could do that at the end. That's fine too. The metabolism of glucose can be represented by the equation here, C6H12O6, etc. Delta H, is this exothermic or endothermic? Exothermic. How many grams of glucose must be metabolized to produce 282 kilojoules of energy? Now this is just dimensional analysis. This kilojoules is for the reaction as written. And so that's how many kilojoules per 1 mole of glucose, per 6 moles of O2, per 6 moles of CO2, and per 6 moles of water. And so we could use this as a conversion factor. And therefore, we're interested in the glucose. And so this is going to be minus 2.82 times 10 to the third kilojoules per mole of glucose, C6H12O6. Or what we could say is it's 2.82 times 10 to the third kilojoules produced per mole of glucose. So what we want is we want to produce 282 kilojoules. So 282 kilojoules produced. And then we see for every mole of glucose, we get 2.82 times 10 to the third kilojoules. And then the molar mass of glucose. Molar mass of glucose, unfortunately, we have to figure that out, which is going to be a pain. We have 6 carbons, so that's going to be 6 times 1201. We have 12 hydrogens. That's going to be 12 times 101. And we have 6 oxygens, which would be 6 times 16.00. So 6 times 12 is 72.06, I think. Is that correct? This is going to be 12.12. 6 times 16 would be 96.00. So this is going to be 18, 10, 180.12. Is that correct?
Yep.
Okay. So let's figure out how many grams. This is going to be 282 divided by 2,820. So I'm just using my phone. Times 180.12. Entering scientific notation is a bit of a pain.
It's 0.18, not
0.18. All right.
0.12 for the grams of glucose.
Okay.
I did get 18.018 grams of
18.01.
8, yeah.
That's what I got. Even with that.
This is an exothermic reaction, correct?
6. Yeah. This is 1 to 8. Yeah. This is exothermic.
I know because it's just to produce.
Right. So rather than negative, I'd say produced.
On the bottom, or
Mhm.
what?
On this one too, produced. Otherwise, I have to change the sign back to negative. You're right. Okay, let's move on. Let's see. Let's try to finish this now. Visible light is a very small part of the entire electromagnetic spectrum.
True.
True. Radio waves always move slower than gamma rays. Radio waves are moving at the speed of light. So if you hear a live radio broadcast, it's pretty much live. They both move at the same speed, but gamma rays are much more powerful photon. 15. Within a continuous spectrum, there are regions of forbidden energies. False.
Everyone continues, isn't it?
Yeah. Incandescent light bulbs produce a line spectrum. This is supposed to be true, false.
How light bulbs?
Incandescent. Incandescent are the old-fashioned light bulbs with a piece of metal. And you get a hot piece of metal, and you heat it up until it starts glowing white hot. And when it's glowing white hot, does it emit the full rainbow of colors, or does it only emit specific colors?
It emits white.
It emits white light. White light is continuous or quantized? Continuous. This is false. Line spectrum would be like the hydrogen lamp, doesn't emit white light. Modern day scientists visualize electrons orbiting the nucleus in a circular orbit. False. Heisenberg's uncertainty principle means we visualize the electron position as a
This is a cloud.
cloud. Orbitals are the solutions to the
Bohr theory.
False.
This is wrong. There's a comment on the board, I think. Orbitals are the solutions to the...
The Bohr model?
No. Orbits are the solutions to the Bohr model. Orbitals are the solutions to the Schrödinger equation or quantum mechanics. Schrödinger equation is what it's supposed to be. So there's supposed to be a list of answers here. Bohr, etc. And then Schrödinger. Schrödinger would be it. 20. When L equals 1, we have the 3 p orbitals. That's false. We have p orbitals, that's true, but not the 3, because we need to know the n. 21, n equals 0 is the lowest energy level. It's false. This is forbidden, according to the Schrödinger equation. 2D orbitals violate quantum mechanics because L is too small. That's false. L is too big. The max is n minus 1. The electron configuration for chromium is, this is true or false?
That's good.
You'd expect it to be true, but it is.
Twelve because
Oh, because of the.
before S1, correct?
It's a-
Yes.
it's an exception.
It's one of the exceptions. This is the half-filled D. Hund's rule states orbitals of the same energy should be filled singly with parallel spin. Excuse me. The electron configuration of the fluoride ion is helium 2s2 2p6. This is true. Fluoride is helium 2s2 2p5, and fluoride ion has an extra electron, so it'd fill first and second shell. Tungsten is xenon 6s2 5d4, so we need the periodic table for this. Do with my periodic table. Oh, shoot. Yeah, tungsten is the symbol W. So I'm looking for tungstens here, it's W. So this is the first, second, third, fourth, fifth, sixth shell. Sixth shell, we can go, we'll fill up the fifth shell. Fifth shell is going to be filled with xenon. So we go from xenon, then it would be
It would be a
6s2. But take a look at what happens to the numbers.
4F.
4f and then 5d. Yeah, so there should be 4f in there.
But 4F is like on the bottom of the chart.
This is false. This is again, sorry, this is true, false. This is false. The 4f are missing. This is not enough electrons. Tungsten has how many electrons? 74. Xenon has how many electrons? 54. 54 plus 2 is 56. 56 plus 4 is 60. This is 60 electrons. They don't match. Which bond is most polar? Yeah, the two that are furthest apart. Hydrogen versus chlorine or hydrogen versus oxygen? Now, chlorine and oxygen, this is a trick question because you would expect them to be equal, but it turns out oxygen's more electronegative. You know what the three most electronegative elements on the periodic table are?
Fluorine, oxygen.
Yeah, fluorine, oxygen, and then nitrogen. Nitrogen is odd because it's smaller. This is chlorine's in the next shell, so it's not as electronegative. Charge on the alkaline earth B. Noble gases are highly reactive.
False.
The bond between a metal and a nonmetal is likely. Metal, like sodium, and a nonmetal, like chlorine, is most likely. Sodium chloride is polar covalent.
Yeah, I think you see it.
Oh, A.
No. Ionic. An example would be like sodium chloride forms an ionic lattice. Sodium chloride consists of the sodium ion and the chloride ion. Chloride has an octet. Remember this? What is the predicted bond angle in CO2? We just did it.
Oh, wait. 180.
Let's see the two ways.
Strong bases ionize in water.
False.
Strong bases hydrolyze in water. They don't ionize.
Acids ionize in water, correct?
Hmm?
Acids ionize.
Acids can ionize, and compounds like sodium chloride can ionize, but bases hydrolyze water, not ionize. What is the predicted bond angle in H2O? 109. This is no distortion. H2O. The tetrahedral bent 109. What is the predicted bond angle in SO2?
What do you think of?
True or false?
False.
False. Ideal would be like 180. No.
No, the ideal would be
120.
120 because of the lone pair. Lone pair is going to prevent it from being 180. What is the shape of ammonia? The shape. When people say the shape, they don't care about the EGG. They want the MG, trigonal pyramidal. The EGG is just a step to get us to the MG. It's not the end. CF4 is polar.
False.
H2O is polar.
True.
All right, this was summer, and so there's some stuff that was combined in this.
Chapter 14.
No, this is earlier. Chemical reactions: magnesium carbonate, hydrochloric acid, lead 2 acetate, and sodium sulfate. I'm not going to put these on. I already tested you on this on your last exam, so let's move over to 39. It's not that you can forget these because these are going to pop up again on the final exam. And so don't ignore them completely. But there's some stuff that's missing here. Well, maybe not. Lewis structures. Oh, there is Lewis structures here. Not really missing. What is the theoretical yield of hydrogen when 32 grams of magnesium is allowed to react with 24.3 grams of 7.00% by mass HCl? And so this is an example of a limiting reagent problem. So I like to do limiting reagent by the comparison of moles or the smaller amount method. Smaller amount method. And so first we're going to do 32 grams of magnesium. And so we're going to assume there's excess HCl. So with 32 grams of magnesium, then let's convert that to moles of magnesium. Magnesium is 24 point what? My vision's My vision isn't so great. So can somebody read that? 0.31 grams of magnesium per mole. Okay, and then we need the balanced equation, which I gave you up here. How many moles of HCl? For every 1 mole of magnesium. So that gives us pure HCl. And then we're going to go to mass. We don't always have to go to the mass here, but the mass is going to be 35.45 plus 101. And so it's going to give me 36.46. So 36.46 grams of HCl per mole of HCl. All right, but we don't have pure HCl. We have 7.00% by mass HCl solution. So what that means is for every 100 grams of solution, we have 7.00 grams of pure HCl. And so that's going to give us how many grams of solution we have. Actually, I don't want that, do I?
Can't you calculate it and you can go to the other one?
I want the yield of hydrogen. This is wrong. Sorry. I could do it this way, but that would be comparison of moles method. And I want to use the smaller amount method. And so which one is going to produce the hydrogen? And so what is the hydrogen ratio? It's a 1-to-1 mole ratio. So 1 mole of hydrogen for every 1 mole of magnesium. And the molar mass of hydrogen is 101 per hydrogen atoms. So that gives us 202, but it's only 3 sig figs. I want 4 sig figs. And so I'm going to use 1008, which gives me 2.016 grams of hydrogen per mole of hydrogen. Okay, this is giving me the product. The product's what I want. So let's do that. 32 divided by 24.31 times 2 times 2.016. Gosh, keys are not working on this. How many grams did you get? 1.990?
You don't need the 2 moles of HCl or 1 mole.
All right, let me try that. Oh, yeah. Yeah, you're right. This doesn't belong there either. And so that's 32 divided by 24.31 times 2.016. 2.653 grams of hydrogen. All right, then B, we're going to go with 24.3 grams of 7.00% HCl solution. Assume excess magnesium. This is assuming excess HCl. So 24.3 grams of solution. In this solution, there are 7.00 grams of pure HCl per 100 grams of solution. One mole of HCl weighs 36.46 grams. And then it's a 2 to 1. So 1 mole of H2 for every 2 moles of HCl. and then 2.016 grams of H2 per mole of HCl, or H2, sorry, per mole of H2. What's that? This pen, I need to make it narrower, but this is as narrow as it gets. So 24.3 times 7 divided by 100 divided by 36.46 divided by 2 times 2.016. Keyed out okay. What did you get? 0.04702 grams. And so the theoretical yield is a smaller amount, 0.0470 grams hydrogen. So this would be the theoretical yield. This would be the limiting reagent. This would be the excess reagent. Theoretical yield. Okay, now how much excess reagent remains? Well, we start off with 32 grams. Since I'm running out of space here, I'm going to just insert it in between these. So this will be calculation C.
It's a theoretical yield because the solution is the limiting reactant.
Yeah. Is 32 grams minus the amount of magnesium used by the LR.
You have to do the value solution with respect to magnesium, correct?
Yes. 32 grams minus, okay, how much was consumed by the LR? 24.3 grams of solution times 7.00 grams of HCl per 100 grams of solution. Oops. Times what? 1 mole, 36.46 grams, pure HCl, times 1 mole of magnesium per 2 moles of HCl, times 30 or 24.31 grams, 24.31 grams of magnesium per mole of magnesium. I ran out of room. So this is going to be 32 grams minus, all right, 24.3 times 7 divided by 100 divided by 36.46 divided by 2 times 24.31, 0.56. 0.567? 1? Okay. Minus 32. 31.43. We have to go by decimal places, and so to round this to no decimal places, we're going to just round it to 31 grams of excess remaining.
It's the trick to identify that this is a limiting reactant.
The limiting reactant produces a smaller amount.
Oh, so what's the indicator for the limiting reactant equation or formula?
I'm sorry?
What's the indicator for it to know that it's a limiting
You don't. In the equation, you don't.
No, that you know you have to use this stuff.
You're given the amounts of two reactants. You're given how much magnesium you have, and you're given how much HCl you have. If you're given both, then if you're only given one, then you don't have any choice. You have to assume you have excess other. But since you're given both, we don't know which one is the limiting reactant. So this is just straight memorization. The 4 P's are all supposed to be in the same line, but it's hard to draw with this. No, but you should, because I want to see up to 4P. I'll probably say up to 4P. Draw it in. You see this?
Have
So we could do the quantum numbers next. Yeah, etc. We can add more info for more points. Etc. means there's more stuff you can put into this. Do you remember doing this in class? And then one 3D drawing we'll have to do. This we didn't do, but this we did. This we didn't do, this we didn't do. Loose structures we did. What's that? Yeah, right. EGG, MG, and then Lewis structures.
Do we have to add the numbers underneath the 4S? Like, do we have to add the 100 and 200?
No. It depends on how many points you want.
Okay, but
If you want more points, add the numbers. If you want fewer points, then don't add the numbers. But it's not always necessary because it's extra.
okay.
We'll redo it. I have to give you a different one probably, or I'll give you the when do you want to redo it?
When can I do it?
You could do it this afternoon, or you could do it tomorrow if you want.
Tomorrow.
Okay.
Interview at the Welcome Center tomorrow
Okay.
between 11:30 and 12.
Okay.
Is it okay if I leave for class?
Yes, yeah, that's fine, no problem. Okay.
Did we get the nomenclature quiz back?
Oh, I'll give it back tomorrow. There's still somebody, a couple of people who still need to take it, so. give it back to them.
For the chapter 11 homework,
Mhm.
it said it also has like stuff from the manual. What is that? Is that all of the quantity?
The supplemental material.
All of it? Like there's like 9, I think.
No, you don't have to turn that in.
No?
Oh, yeah, ask me tomorrow. then
Okay.
I'll
And then
tell you.
also I wanted to ask which labs are due tomorrow?
No labs are due.
None tomorrow?
No.
Awesome. Okay, thank you.